In this video, we're going to consider some non-Euclidean geometries for the first time. So now we're going to drop our assumption of the parallel postulate that given any line and a point, there's exactly one line through the point parallel to the original line, and start looking at situations where that assumption is not necessarily true. This can be difficult to conceptualize and intuit, and so one of the first things that we want to look at is a basic model of a non-Euclidean geometry. We're going to be looking at the Poincaré model, which is one of the first non-Euclidean geometries to really be studied in depth. And it's a geometry which is going to satisfy all of the axioms of our geometries until you get to the parallel postulate. And then we're going to see that it does not satisfy the parallel postulate, proving, among other things, that the parallel postulate can't be proved from the other axioms that we have. So, the Poincaré model is going to be built inside a Euclidean plane. So let's let E be a Euclidean plane. That is a plane in a geometry which does satisfy the parallel postulate, one that we're familiar with. And let's let CP1 be a circle. Let's give that the name C. And let's let S be the interior of the circle C. This S is going to be the set of points in our Poincaré model, the set of points in our new geometry. So we're going to define a geometry G. Now, to define the geometry, I need to tell you a few things. I need to tell you what the points are, the lines are. We're going to be working in just a single plane here, but I also need to tell you what the distance measurements in the geometry is, and what the angle measure is. So we're going to get this geometry G, which is going to have a set of points, a set of lines, it's going to have a distance, and it's going to have an angle measure. And I need to describe to you what each one of these four elements are. Now, the first one is the set of points, as I already mentioned, is just the set of points inside the circle C. So we've got the circle C, we've got the center here. We taking a circle with radius 1, and so the inside of this circle is the set of points in our geometry. Notice we're only considering the points in the interior, not on the circle itself. So the geometry G that we're considering here doesn't actually include the points on the circle. And then I need to describe what the lines are in our geometry G. The lines L are of two kinds. They can either be the intersection of a Euclidean line L that goes through P and S. So if we were to take a Euclidean line that sits in our plane and happens to go through the point P, and then just get rid of all the things that were not inside our geometry, this would be one example of a line in the Poincaré model. So it's sort of a diameter of the circle without the endpoints. So that's the first kind of line in our geometry G. And the other one is the intersection of a Euclidean circle C prime and S if C prime is orthogonal to C. And let me just illustrate what that means. So if I were to take a circle, let me try and do this carefully. If I were to take some circle C prime that lies in our Euclidean plane, and I look at the intersection with C, we're going to call the two circles orthogonal if these two intersections have the property that the tangent lines, the two tangent lines at this point, are perpendicular to one another. So each one of these lines has each one of these circles rather has a tangent line at the point of intersection, and we call the two circles orthogonal if those tangent lines are perpendicular at their points of intersection. And so that gives us the other kind of line that exists in our Euclidean plane. It's these segments of circles that that intersect with the interior of the circle C, but they have to be circles that are orthogonal to the main circle C. Now, one thing that I will point out, which you can see in some of the details of this construction, which I'm going to leave for the notes, is that one can show that the circles CPR and the circles CP'R' are orthogonal if and only if the distance PP' squared is equal to r squared plus r prime squared. So the picture here is that if the two circles are orthogonal to one another, then the tangent lines being orthogonal to one another means that the triangle that's created between the two centers of the circle and the point where they intersect one another is a right triangle. And that occurs exactly when you have this relationship between the distances between the centers of the circles and the radii of the circles. So let's look at some properties of the Poincaré model before we get into defining distance and angle measure. The first, which requires some work, which, as I say, you can find in the notes, is that axiom I1 holds. Remember that axiom I1 said that given any 2 points, there exists a unique line containing them. So if I just take 2 random points in our geometry, then there should be a unique line that contains them. And if we're talking about our new Poincaré geometry, then the line that contains them has to be the intersection of a circle orthogonal to C that contains both of these points. One can construct this. Basically, what one does to construct this, if you just have A and B, is you construct the segment between them. Then you construct the perpendicular bisector of that segment in the Euclidean sense, the perpendicular bisector in the Euclidean sense, and the segment between them in the Euclidean sense. And then you show that there exists a point on this line that that has the correct property, that where if you construct the circle with center at the point P prime and passing through the points A and B, then that circle will be orthogonal to the original circle, C. And so, given any 2 points in the Poincaré model, we can come up with a line, a unique line containing them, a unique Poincaré line connecting them. So let's talk about how we define distance in order to make sense of a lot of the geometric things that we've done. We need to know what the distance is between 2 points, and that's what allows us to define things like segments and so forth. So to do that, we're going to use this line that contains the points A and B. So to define the distance d between 2 points A and B, let's let C prime be the circle, the Euclidean circle, I should say, containing the Poincaré line containing A and B. Then let's let R and T be the points, the set R and T be the intersection of the circle C with the circle C prime. So we've got these points R and T, and these are not points in the Poincaré geometry, but they are points in the Euclidean geometry, so we can refer to them. Now let's define the distance from A to B to be the following number. It's going to be the absolute value of the natural logarithm of the distance from A to R divided by the distance from A to T divided by the distance from B to R divided by the distance from B to T. Now, this is definitely not an obvious thing to construct. In fact, coming up with the proper way of determining distance on the lines in the Poincaré model is possibly one of the most difficult parts of the whole process. Fortunately, that was done some time ago, and so we can use this definition. And so there are some interesting things that we can do with it. So we've got that the distance from A to B, first of all, it doesn't depend on R and T. If we exchange the roles of R and T, it turns out that we get the same result. This is the same as the absolute value of the natural logarithm of AT over AR divided by BT over BR. As it turns out, if you look at the two logarithm expressions, by exchanging the roles of R and T, they're just the negatives of one another. And so because we're taking the absolute value, we always get the same number out of it. So the points R and T are uniquely determined. Their order isn't, but their order doesn't matter for defining the distance between A and B. Now, we want to know that this distance satisfies all of our distance axioms. And it does. This distance satisfies all of our distance axioms. And the easiest way to show that is to show that we have the ruler postulate, is to show that we can construct a coordinate system on every line that that respects this distance, and that that function is not super surprising. It uses the same formula as the distance here. So we can construct a coordinate function on the line AB, where this is the Poincaré line. And we can do it in the following way. For any x in the line AB, we can let f of x be pretty much just the expression that we had up above here, where we take the distance from x to r over the distance from x to t over the distance from b to r divided by the distance from b to t. And this function does in fact give us a coordinate system for the real or for the line AB in the Poincaré model, which can be checked fairly easily. One of the immediate consequences of this, which is a little bit surprising intuitively as we look at the Poincaré model, is that when measuring distance using the Poincaré distance, lines are in fact of infinite length. This coordinate system F does in fact create a bijection between the real numbers and this line going through AB, this Poincaré line going through AB, that is bijective and respects the distance formula, which means that in fact, as we start looking at points that are, say, closer and closer to D or closer and closer to R, those points actually do get further and further and further away from, say, A or B. They get arbitrarily far away from either A or B. So, from the point of view of someone living inside this Poincaré universe, this line going through A and B is in fact infinitely long. People inside the Poincaré universe don't see a boundary. As far as they're concerned, you can walk in as far as you like, an arbitrary distance in any direction. And that's because we've got this this scaling property that's happening as we move from looking at things in a Euclidean way to looking at things in the Poincaré model. I find this somewhat profound that, whether or not a space is finite or infinite in some dimension, in some measurement, depends entirely on whether, or can depend entirely on whether you're living inside it or outside of it. Those of us looking outside the Poincaré model can see that it all lives just inside this little circle with radius 1. But from the point of view of everyone inside it, it's a literally infinite universe that goes on forever because of the way the distance works for the points that live inside the Poincaré geometry. So I find that somewhat interesting. I'm not going to philosophize here, but there are some fun analogies that one can make. It turns out that the Poincaré model also has plane separation. This one is a little bit harder to prove, but intuitively we can see that it makes sense. So if I've got my Poincaré geometry and I've got some line in the geometry, most of which look like this, well, then we can identify two sides of this line. Remember that for our plane separation, we wanted to say, given a line, we need to be able to identify two half planes that have that line as a boundary. So we could call this side H1 and this side H2. And so we actually have that plane separation axiom PS1 also holds. So the fact that we have distances holding means that we have all of our betweenness statements. All of our betweenness theorems hold in the Poincaré model. We have plane separation, which means that all of our statements about like the interiors of triangles and the Pasch postulate and lots of these results, they all hold as well. We can talk about angles, and we can talk about the interiors of angles, and the fact that we have betweenness means we can talk about rays and segments and all these things that we've been studying the entire semester, all exist within the Poincaré model. So plane separation holds. Now, before we move on and look at anything else, we need to talk about angle measure. How is angle measure defined? If we take a couple of lines in our model, that intersect, then we can construct the rays. We can construct a couple of rays. So for instance, one of the rays that we could look at would be this one. Here's a ray in the Poincaré model. And then here's another ray in the Poincaré model. And they're what you get by taking a point on a line and then including all the things that are on, one side of that point. Now, what we can do is define the angle measure of this angle. Let me give these some points that we can talk about this angle precisely. So we've got the point B, point A over here, point C over here. So we have that the angle ABC exists based on the betweenness and everything else that we've done before. But we want to know what's the measure. And the way that we get the measure is that we take the tangent lines to these two circles, the Euclidean tangent lines to the two circles defining the lines AB and the lines BC, and we look at the angle between them. So angle ABC has measure equal to the angle of the Euclidean angle formed by the tangent rays of the circles defining the Poincaré lines AB and BC at B. So we can look at the two Euclidean rays at B that are the tangents to the circles here, and measure this angle, and whatever the measure of that angle is the Poincaré measure of that angle as well. So we define the Poincaré measure in terms Poincaré angle measure in terms of the Euclidean angle measure. There are lots of interesting things we can see here, and this is where we can really start seeing a lot of differences between the Poincaré model and the Euclidean model. So, for instance, we can draw some very extreme uh, angles here. We can take some lines that intersect very, very close to the edge of the Poincaré model and get something like this. This straight line through would have to go through the center P of the circle. And notice that if we take these three lines, we can identify a circle out of it because we've got a point of intersection here, point of intersection here, point of intersection here, and so we can look at the triangle ABC. But also notice that the actual angles being formed at A, B, and C are all very, very small. By moving out close to the edge of the universe here, close from our perspective, of course, from the Poincaré perspective, everything's infinitely far away from the edge. But from our perspective, by moving further and further away, we have narrowed these angles together quite a lot. And so, in fact, we can see just from this example that the sum of the measures of the interior angles of this triangle ABC is certainly going to be a whole lot less than 180. In fact, one might expect that as you push the points A, B, and C further and further out towards the edges of the universe, that the sum of the total angles inside is going to get smaller and smaller and smaller. And in fact, that's true. We can make that sum of angles as small as we want, which we'll see in a little bit. However, despite all this weirdness, it turns out that the side angle side postulate holds, which means we have congruence of triangles, we have side angle side, and all the things that come from that. So we have side 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 holding, we have, angle angle side holding, and all of the other congruence axioms that we had before. We don't have similarity at this point because remember that we only defined similarity after we were working with the parallel postulate, which we aren't working with here. Now, proving that the side angle side postulate holds is fairly complicated, so we won't do that here. We'll sort of take it for granted. So what we've seen, or what I've asserted anyway, is that all of the axioms of our geometry up until the parallel postulate hold in the Poincaré model. They all hold. So the question is, well, okay, does the parallel postulate hold? And the answer is resounding no, absolutely not. It is not the case that the parallel postulate holds. The parallel postulate fails completely. So, for example, let's take a line here. This is a line in our Poincaré geometry. And let's take the point P to just be the center of the circle. Now, we want to know how many lines are there that go through P and are parallel to L. We know there always exists one. We proved that long before we talked about the parallel postulate. There always exists at least one parallel line through P, but there is not just one. So there's one line that goes through P and is parallel to L. There's another one. And there's another one. And there's another one. And all of these lines are parallel to L, because remember, the definition of what it means to be parallel is that the two lines don't intersect. And all of these lines that we've drawn through P all do not intersect the line L, which means that these lines here, these are all parallel to the line L. And in fact, there's not just more than one. There are infinitely many. There are infinitely many parallel lines through L, the parallel postulate fails completely. And this is one of the things that we're going to see when we start looking at non-Euclidean geometries, is that if the parallel postulate fails even a little bit, it fails completely and it fails everywhere. So this is the Poincaré model is a very good one to keep in mind. We're going to continue coming back and referring to it when we need a picture or some intuition about what's going on with a non-Euclidean geometry topic.